So I'm not exactly sure what just happened there, but my sound seemed to have, or my video seemed to have cut out at this point. So we solved the equation. We can't solve this by algebra because the nature of the equation, you have an embedded x and an x outside the log. So we have to solve this by graphing, and solving by graphing I get these values. X equals 0.49. Once I do that, I can plug the x back into my y equation to solve for y. So that's how I got my negative 0.24. Okay, so for the next one, this is a minimization problem. So I have a pop can and I want to make that, use the least amount of material to make a 355 milliliter cylindrical pop can. So if I'm going to minimize the material is the surface area. So I want to minimize the surface area. So I've generated my surface area equation here. I have too many variables. I've got an R and an H to be able to differentiate that. So I need to find another relationship. The relationship is the volume. And the volume is going to relate the R squared to the H. And when we do that, we can rearrange it and just make an expression for H, which then we can replace into the original equation. So I'm going to plug that into there and simplified it looks like that. So now I have my expression for surface area. I'm going to differentiate it, and since I want to optimize it, I'm going to make it equal to 0 and solve that equation. So solving that, you get a radius equals the cube root of 710 over 4 pi. We can solve then the surface area by plugging into my surface area formula, which is this one right here. Now we could plug it back into this one, but then we'd have to solve for the H. So I'm just going to, since I just need R in this equation, I plugged it into here, and that worked out to be 209.14 centimeters squared. Okay, so let's take a look at the next one as well. So the function is moving as position on, looks like this is what we call rectilinear motion, where it just kind of moves back and forth along a horizontal line. And the position of that point is given by this t equation based on t equals time. So, it says find p of t and v of t when acceleration is 0. Well, to do that, I need to actually differentiate to find the expression for a of t. So I'm going to differentiate once, and then I'm going to differentiate again to get the acceleration. Okay, and I want to solve for the t when acceleration is equal to 0. So time equals 2. So p of 2 then works out to be, when I plug 2 in, it's 8 minus 24, which is negative 16, plus 1 is negative 15. So that's my position. The velocity at that point is going to be, I plug it into my velocity equation, I get 12 minus 24, which is negative 12, maybe meters per second, depending what the units are. So same problem, but now I'm just going to solve when v is 0. So when v of t is equal to 0, I solve that quadratic equation. So I'm going to factor out my 3t. Okay, and that's when v is equal to 0, when t is equal to 0, or when t is equal to 4 seconds. Okay, so then find the p of t, p of 0, p of 4. P of 0 is equal to 1. The p of 4 is going to be, what's that going to be? 64 minus 6 times 16 is 96. So 64 minus 96 is negative 32. Plus 1 is 31. So the acceleration at 0, when I plug 0 into my acceleration formula, it's negative 12 meters per second squared. And then acceleration at 4, I'm going to get positive 12 meters per second squared. Okay. I think this is the last problem, and this is a fairly um, typical calculus problem. There is an applet. If you follow that link, you can see the applet kind of visualize what's going on. But this person is, if he's 6 kilometers from the shore on the water, and he's 10 kilometers from that point on the land to point B. He's trying to get from A to B. Now the shortest distance is going to always be a straight line, but if he does that, he's going to be swimming the whole time, and he can't swim faster than he runs. But if he goes straight here and minimizes swimming, he's got the most distance that he's going to travel here. Okay? He's going to go maximize amount of time on land, which is good, but he's also going the furthest possible distance if he does that. So somewhere in between is going to optimize his time. Okay, so first of all, we just need to make sure that we remember that our little triangle, right? The distance is velocity over time. Okay, so if I want to minimize time, so if they need to get from what angle normal should they swim, so they want to go get there the fastest point, the fastest way they can. So we want to minimize time. So I need an equation for time. So time on the water is going to be the distance on the water over the velocity on the water. Time on land is equal to the distance on the land over velocity on the land. Okay, so you've been given the velocities on water and land. We just need to figure out distance on water and distance on land. Okay, so this is going to be, I'm going to set this up this way. I'm going to call that x. And the distance on the land is straightforward. That's going to be 10 minus x. Okay, so I'm just going to rewrite that. So time on land is going to be 10 minus x over the velocity on the land, which is 15 kilometers per hour. The distance along the water is going to be that distance there. In terms of x, well, I can say that that's going to be x squared plus 6 squared equals that squared. So that's going to end up being 36 plus x squared square root. Now notice that I'm doing it in terms of x and not theta. I could do it with theta, but it's probably easier to do with x, and once I find x, I can just find theta by using, in this case, probably arctan or something like that. So that's what I'm going to do. So my time on water is going to be the distance on the water, okay, 36 plus x squared over the velocity on the water, which is 3. And I want to minimize that total time. Okay, so I'm going to write the equation. So my time total is going to be the time on the water. So here's my time on the water plus my time on the land. So the distance divided by velocity on the land, which is time. And I want to find the minimum time, so I'm going to differentiate this. So I'm going to end up with 1/3, 1 over 2 square root 36 plus x squared times 2x using chain rule. This is going to be, well, that's 10 over 15 constant, which is 0. So I'm going to differentiate negative 1 over 15 times x, or my slope is going to be negative 1 over 15. And I want to find out when that's equal to 0. Now I have my equation. I'm going to simplify this a little bit. So my equation equal to 0, I'm going to end up with x over 3 root 36 plus x squared, and that's equal to 1 over 15 on the, I'm just going to move that 15 to that side there. Okay, and solve this equation. I'm going to end up with 5x equals square root 36 plus x squared by cross multiplying that. Square both sides to solve for x. So I'm going to end up with 24x squared equals 36. x squared equals 3 over 2. So x is equal to plus minus square root 3 over 2. Okay, so we're gonna go really kind of pretty sharply that way. Okay, so then if that's equal to 3 over 2, I still need to solve for theta. So theta is going to be the arctan of opposite root 3 over 2 over 6. So calculating my theta. Okay, for my calculator, what am I going to get here? I'm getting an angle of 0.201, so I'm going to round that to 20 radians. Okay, so that angle in here at 0.02 is going to give me the best angle to minimize the time to get there from A to B the fastest.